Hello, my name is Gustav Vogels. I'm an electronics developer. First, I would like to apologize for my poor English, but I try as best as I can. In this YouTube post, I want to share descriptions and hands-on demonstrations of how the microcontroller device works. In this case, the microchip ATMEL AT89S52. Personally, I am one of those people who have always understood complex processes and connections best or more easily when the processes were attached to a concrete example. That's how I keep it here in this tutorial. The demonstration example in this tutorial should be the realization of a running light with 8 LEDs, in which, as the final stage of the realization, the microcontroller AT89S52 takes over this function. First, some definitions of terms. A microcontroller is a microprocessor that also contains peripheral functions. I look at the microcontroller under the premise that this is an integrated circuit and not a classic computer. Furthermore, I only consider the microcontroller in its native version, which means without any pre-programming by the manufacturer. A bootloader or similar is not required for the demonstration example in this tutorial. As already mentioned, a running light with 8 LEDs is to be implemented as the end result in this demonstration example with a microchip ATMEL AT89S52. The AT89S52 is an 8-bit microcontroller with 8K bytes of program memory. All other statements and dimension designations in this tutorial refer to this or an equivalent 8-bit microcontroller. As with any further training, however, a certain basic knowledge is essential. You should already be familiar with digital logic functions such as gates, inverters, flip-flops, counters, monoflops, latches, shift registers, multiplexers, decoders, and so on. But first, you have to be able to think up a basic control or to work it out. It does not matter whether such a control is implemented with relays, with transistors, with logic modules, or with a microcontroller. The more talent someone has in this regard, the easier it will be for them to develop any kind of controls. Back to the running light. Appropriate hardware for realizing the task must first be developed. Here is my circuit contribution regarding this running light with 8 LEDs. The focus is on the AT89S52 microcontroller here in the PDIP-40 design. I connected the 8 LEDs to ports P0.0 to P0.7 via current limiting resistors of 2.2 kilo ohms. I intended port P2.0 as a test output. The oscillator circuit integrated in the microcontroller is completed with a 6 MHz crystal and two 22 picofarad capacitors. The L387A voltage regulator not only ensures a stable 5-volt power supply, it also generates a negative reset signal when the power supply is switched on, which is negated and fed to the microcontroller via a transistor. That's all there is to hardware circuitry. Here is the modest number of components with which the circuit, respectively the hardware, is to be set up. After building the circuit on a Duro cardboard, my running light variant now looks at this. I create the software, respectively the program, with a PC on which the Intel AT51 assembler is installed. The program data created then get to my EEPROM simulator in the form of the Intel hex format via the RS-232 interface. The data is then available on this 28-pin dual inline IC connector. To test the program, I use a special microcontroller of the MCS51 series, namely a piggyback-microcontroller by the manufacturer Harris Semiconductor. This microcontroller leads its ROM area in the form of a 28-pin dual inline socket to the outside. In this block circuit picture, I only draw the components that are necessary for the functional realization of the running light. In principle, I left out any ballast that is not necessary for the basic understanding. The drive of the entire functional process is the 16-bit program counter. This program counter continuously receives impulses from a quartz oscillator. If one would not intervene in this process, the program counter would count up to 65,535 and then continue again at 0 and so on. This program counter counts exclusively in one direction, namely upwards. The first intervention in the program counter's counting process is carried out by a so-called reset circuit. This means that when the power supply is switched on, the reset circuit ensures that the program counter always begins its counting function with the counter side 0. The control unit, respectively the central unit, can make a further intervention in the counting process. Depending on an instruction, it can set the program counter to any number of counts. The program counter then continues counting from the preset count. The 16 outputs of the program counter represent the 16-bit address bus. With the AT89S52, the first 8,192 counts point to the program memory. A decoder ensures that with all higher counter readings beyond this 8,192, the program memory cannot be selected at all. If the system is switched on and the program counter is set to the value 0 by the reset circuit, the first memory location of the program memory is addressed via the address bus. The program memory then transfers its memory contents, which it has stored at the address 0, to the data bus. The control center of a microcontroller is the CPU, Central Process Unit. Here, in the demonstration example of the running light, the 8-bit data content at address 0 is 00000010 binary. This is an instruction. This instruction 00000010 binary is fed to the CPU via the data bus. The CPU's MCS51 core interpret this binary value to ensure that the program counter is set to a specific value after execution of this instruction. This executes a program jump. How far and where the jump should go is written in the two memory locations that follow this instruction. The MCS51 core also know this because of the previous instruction. These are the two program memory locations that are addressed under program counter contents 1 and 2. The content of these two program memory locations determines the weight of the program jump. Thereafter, the program counter will then continue its count with this predetermined counter reading. This is called a jump instruction. This jump command, respectively, this instruction is 000000010 binary at the MCS51 core and is an unconditional long jump. This data interpretation, respectively, this data processing structure, such as this jump command and the subsequent program executions, was developed by the Intel company according to the Harvard architecture and was first presented with the 8051 microcontroller in the year 1980. Intel later licensed many manufacturers to use this function core developed by Intel. This is also the case with the AT89S52. Inside, this microcontroller beats the heart of a microcontroller that is more than 40 years old. I would like to emphasize here that the microcontroller only understands these binary instructions, nothing else. All other forms of instruction input must be processed with the help of translation programs in such a way that this binary format comes out again at the end, which the microcontroller understands. In the early days of microprocessor and microcontroller applications, only a few companies had the appropriate development systems. That's why I developed a programming box at this time with which the EEPROM, respectively the program memory, was simulated via a RAM memory. The individual instructions were entered directly under each address using a hex keyboard and shown on an LED display. It couldn't be more direct or immediate. However, this programming method is not convenient. On the contrary. Later, when the PC became general, programming was done using assembler. When assembling, the assembler made instruction 02 hex code from the assembler mnemonic LGMP long jump, and this corresponds to the binary value 00000010. The huge advantage of programming with the help of an assembler compared to the hex code input is that you can insert new program parts at any point in the program. The assembler recalculates all addresses and the associated data during assembly. The processing of the data takes place via so-called registers, implied here. The data transferred in these registers can be manipulated, processed, and logically linked with one another using instructions from the CPU. Data that need to be cached because you need it again later in the program execution is cached in random access memory. The CPU can manage the data to be taken out of the system or required input data via ports. I have come up with a suitable control system for realizing the running light. According of saying, many roads lead to Rome is also the case in this demonstration example. The solution to the control task I have presented here is just one of many other options. I would like to describe the procedure I have devised. I designed this chaser control as a subprogram. To run this subprogram, I used 3 8-bit memory locations from the RAM area. A memory location that acts as a bit register, a memory location that acts as a prescaler, and a memory location that is used as a shift register. I use the prescaler because without it the running speed of the running light would just be too fast for me. A flag is a 1-bit storage location within a byte. If this memory location has the value 1, the flag is said to be set. If the memory location has the value 0, the flag is said to have been deleted or not set. What you have to know in advance is that this subprogram is called up regularly and that there is a 100 millisecond flag which is repeated elsewhere in the program every 100 millisecond set. Later I will show where and how this 100 millisecond flag is set. After calling the subprogram running light, the first thing to be queried is whether this 100 millisecond flag is set. If not, the processing of this subprogram has already ended here. If it does, the 100 millisecond flag is first cleared. Then it is queried whether the content of the prescaler is equal to 2. If not, the content of the prescaler counter is incremented by the value 1. After that, the subprogram running light is exited again. However, if the content of the prescaler is 2, then this prescaler counter is first cleared and then a query is made as to whether the content of the 8-bit memory location which acts as a shift register has the value 0. If the memory location used as as a shift register had the value 0, the value 1 respectively, the binary value 000000001 is then immediately loaded into it. If the memory location used as a shift register not have the value 0, the content of this memory location is shifted one position to the left. Thus, a 1 is shifted step by step every 300 milliseconds through the shift register, until finally the 1 falls out of the shift register and the contents of the shift register are therefore equal to 0. Finally, the content of this memory location, which acts as a shift register, is transferred to the port to which the LEDs are connected. I would like to explain and describe the microcontroller components and how it works. Programming the instructions in assembler gives a direct and immediate influence on the registers and other components of the microcontroller, which makes the functional description of the microcontroller more understandable. Actually, I've already said everything about how the running light works. But I didn't say how to get quartz-stable even-time sequences. As far as timing is concerned, the running light should run in regular time steps. It is an advantage that the microcontroller is driving by a quartz resonant circuit. In order to explain these processes, I cannot avoid going into the subject of interrupts. An interrupt, no matter where it is triggered, initially causes the program counter to be suddenly loaded with a specific value, respectively a specific address. This means that the microcontroller immediately interrupts the task it is currently doing. It follows that every possible interrupt has an unchangeable entry address with which the program counter is loaded if an interrupt is triggered. As a precaution, it should already be mentioned here that the address areas in which these entries can take place must remain reserved for this, and that no other program executions may take place there. Here, with the AT89S52, the program counter addresses from 3 to A3 hex must therefore be kept free. Here is something aside. If the microcontroller has to interrupt the routine it is currently processing due to an interrupt, the following must happen before interrupt processing starts. Important data that has accumulated up to this interrupt must be backed up or saved so that after the interrupt has been processed, the microcontroller can continue where it was interrupted before the interrupt routine. With the saved data, the microcontroller can then continue with its program processing. At that point, where it was previously thrown out by the interrupt routine without data loss. The memory area in which this data is temporarily stored or saved is called stack. If the microcontroller program starts after the system is switched on via the reset signal at program address 0, a jump command is sent to the program counter address 100 hexadecimal. I called this entry point init. With this program jump to the program counter address 100 hexadecimal, which I arbitrarily determined, the program generously skipped the entire range of possible interrupt entry addresses. The initialization phases of the microcontroller program begins at the program counter 100 hexadecimal, respectively init. In this case, the initialization phase means that the necessary settings are made once before the actual program execution. In the first step, the stack pointer area is defined. Data to be backed up is stored here, starting with the RAM area 08 hexadecimal. Then it is determined in which operating mode the counter timer T0 should work. An interrupt release follows for the counter timer T0 and then a general interrupt release. Finally, the counter timer T0 is started. At the end of the initialization sequence, 3 memory locations that have been used are deleted. That's all. Then the program enters its main loop, which I have called main. As you can see, nothing happens here at first. But the timer T0 counter was started in the initialization phase. After counting up 65,535 counts, it triggers an interrupt and thereby sets the program counter to the value 0b hexadecimal. There, at program count b hexadecimal, is the long jump instruction to an entry point I've named MSK100. Once there, all relevant data is first saved. Then the timer T0 counter is loaded with the value 3CAF hexadecimal. As briefly mentioned, I use port P2.0 as a test output. Here, at this point, this port is negated. This means that if the port had high potential up to then, it now has low potential and vice versa. After that, all saved data is restored and the interrupt routine is terminated until the next interrupt. What I have not yet described is why the timer T0 counter is loaded with the value 3CAF hexadecimal or 15,535 decimal. The binary counter integrated in the AT89S52 with the name timer T0 should trigger an interrupt every 100 milliseconds and thus regenerate a quad-stable 100 millisecond routine. The binary counter timer T0 counts up. What happens during the first run of the program after switching on the system? The interrupt is triggered by the timer T0 counter when FFFF hexadecimal overflows to the value 0000 hexadecimal. In the interrupt sequence that follows, the timer T0 counter must then be reloaded in such a way that a new interrupt occurs after every further 100 milliseconds. The process then continues. Due to the internal structure of the AT89S52 microcontroller, 12 oscillator cycles are required for the timer T0 counter to advance by one counting step. The counting frequency of counter timer T0 is therefore lower by a factor 12 than the quartz clock frequency. 6 MHz crystal clock frequency divided by 12 gives 500,000 Hz. 500,000 cycles per second are equivalent to 50,000 cycles per 100 milliseconds, respectively the target time span. The 16-stage counter timer T0 can count from 0 to 65,535, which corresponds from 0 to FFFF in hexadecimal counting. Of the 65,535 maximum possible counting steps, however, only 50,000 counting steps are required to cause interrupts with intervals of 100 milliseconds. For this reason, the timer T0 counter is loaded with the value 15,535 immediately after an interrupt, and thus skips 15,535 counting steps in one fell swoop. It then needs exactly 50,000 upward counting steps up to the maximum end reading of the timer T0 counter of 65,535, and thus exactly 100 milliseconds, which then leads to a new interrupt. The decimal value 15,535 corresponds to the hex value 3CAF. The timer T0 counter is loaded with this hex value in the interrupt program section. A new interrupt is then triggered again and again every 50,000 counting steps, respectively every 100 milliseconds. In order to be able to check the whole thing, I use the port P2.0 as a test output and connected an oscilloscope to it. This exclusive OR instruction causes the potential state of the port P2.0 to be negated with each entry into the interrupt routine. A reference mark on the grid foil corresponds to 50 milliseconds. You can clearly see that after two reference marks, which corresponds to 100 milliseconds, the potential at port P2.0 is negated. Instead of negating the test output, I now use program steps here that set the flag called 100 millisecond flag each time this interrupt related subprogram is called. Here in the main loop main, the subprogram running light is now called. After the call, it is first queried whether the 100 millisecond flag was set in the interrupt routine or not. If it was not set, there is an immediate return from the subprogram. If the 100 millisecond flag was set in the interrupt routine, it is first cleared. During the operation, further possible interrupts are always prevented. This is not absolutely necessary in this program example, but it makes sense to do it this way in most cases. Then the content of the prescaler counter is queried whether it has already counted up to 2. If not, the content of the prescaler counter is incremented by the value 1, and then the subprogram is exited. If the prescaler counter has already reached the value 2, it is first cleared. Then it is queried whether the content of the memory with the shift register function is equal 0. If this is not the case, the content of the memory is shifted one position to the left using a shift command. However, if the content of the memory with the shift register function is equal to 0, the value 1, respectively 000000001 binary, is loaded directly into the memory with the shift register function. Before the subprogram is terminated, the negated content of the memory with the shift register function is transferred to the port P0. The created microcontroller program is first assembled and then transferred to my EEPROM simulator. Now the program test takes place with the piggyback microcontroller, and as you can see, the running light works as expected. But this is not the final result. I want to load the developed microcontroller program into an AT89S52 and check if it also works in this type of microcontroller. There are numerous programmers on the market that made this possible. Personally, I have developed and built my own copying station for such task. In this 0 force IC socket, I plug the 28-pin dual inline IC connector of the EEPROM simulator, and in this 04 IC socket an unprogrammed microcontroller AT89S52 is placed. After entering the correct specifications, the programming process takes place. The now programmed microcontroller AT89S52, or as it also called the flashed microcontroller, is now used in the experimental setup. Lo and behold, everything works. An 8 LED running light. Then, once again, a brief consideration of the complete microcontroller program. When the system power supply is switched on, the program counter starts with the address 0. In order to prevent any possibility of collation with the interrupt entry area, a jump is made to the program counter address 100 hexadecimal, respectively to the init entry point. The initialization phase then takes place there. After initialization has taken place, the main loop main is then continuously processed. The subprogram LAGULA is then constantly called within the main loop main. Here at the entry point MSK100, the program is processed with each interrupt by the counter timer T0. And that was about it. I hope I was able to explain in this tutorial how a microcontroller works in principle. I thank you for your interest and say goodbye in a friendly manner.